magnetic resonance. So NMR theory and simple classical explanation for the relaxation mechanisms, spin and spin lattice interactions. Later on, we will move on to the other nuclear instrumentation and other applications. And block equations and importance of chemical shift. So this nuclear magnetic resonance is already, you might have heard about the MRI technique. So that the MRI is nothing but nuclear magnetic resonance imaging. So nuclear is dropped and magnetic resonance imaging. With that, we are getting many clear and vivid imaging of our different tissues and brain, how it functions, and so that type of a application we are getting from the nuclear magnetic resonance. So nuclear resonance, magnetic resonance spectroscopy, it gives an explanation how the electron environment around the atoms present. So not all, but some atoms, if they place in a strong magnetic field, their nuclei behave like a tiny magnets, aligning themselves with the strong magnetic field. So see, this is the south and north pole, and these are all atoms are kept in a strong magnetic field. And we will see what is the external magnetic field's influence on the nuclei. So they will try to reorient their spins in a differently. So that is the basic concept behind the nuclear magnetic resonance imaging. So electrons behave like this. Both electrons and nuclei are said to possess spin. So this nuclei has also a spin. So any spinning electric charge, usually you can expect an associated magnetic field. So just as electrons with opposite spin pair up with each other, similarly, the protons and neutrons within the nucleus also, they will have a opposite spins will pair up with each other. If a nucleus has even number of protons and neutrons, so let us take an example of a carbon. So it's a carbon's atomic number 6 and mass number is 12. So you have a 6 protons and 6 neutrons, and atom will consist of a 6 electrons outside the nucleus. So the magnetic fields cancels each other and there is no overall magnetic field. However, the number of protons and neutrons is odd. So here it is an even number of protons and even number of neutrons. If you consider the odd number of neutrons or protons within a nuclei, so what will happen? It has some net magnetic field. So such a substance, if you place in an external magnetic field, so nuclear magnet lines up with the external magnetic field in the same way as if you keep a compass in an external magnetic field. So this is how it will try to reorient in the magnetic field. So this is, they will align in a low and high energy things. Okay. So further, we will see how this will. Okay. So that means the nucleus change to a higher energy alignment as well as a lower energy. So if you supply some energy, that energy will be absorbed, and that corresponds to a radio frequencies. So whatever that energy we are supplying in the radio frequency range, and that frequency of energy depends on the environment of the nucleus, that is on the other nuclei and electrons in its neighborhood. So whatever it goes to the higher energy, when it will go to the higher energy, because of we are supplying some energy. What type of energy you are supplying? That is a radio frequency. That is a RF frequency energies or radio waves. So with that frequency, that precise frequency of energy depends on the how much it absorbs that energy. That depends on the environment of the nucleus. So the nucleus environment is, you can describe with the electrons, how the nuclei are surrounded by electrons. So by this, if that sample is examined in a strong magnetic field, that means if you keep this type of a sample in an external magnetic field, and if you measure the frequencies of radiation, how much it absorbs, that information we will get the finally the environment of the nuclei in the molecule. So that means how the electrons are surrounded. So that's, you can map and you can imagine and you can get a image because of the different image processing technologies. So this is the background of what nuclear magnetic resonance. So that means, so because from this unit, you are going to explain after completion of this concept. So what is a, from where, how the nuclear magnetism arises. So how the nucleus is behaving like a magnet. Not all, that light nuclei will have a more this tendency. And what are the different types of magnetic nuclei, and how do you identify different nuclear probes? So you have a proton NMR and different techniques. Okay. And describe the magnetic interaction between external magnetic field and the magnetic nuclei, and the magnetic dipole transitions among the energy levels due to interaction of this radio frequency or radio waves of a certain frequency. And we will solve the problems in NMR using that coordinate system. And this is finally how we are using this to map the tissues of normal and malignant. That means a type of a carcinogenic tissues. If it presents in a human body, that you can identify. So all this by applying some relaxation mechanisms. By applying some relaxation mechanisms, you can get the more information. Okay. So this is how you are sorry, yeah, briefly discuss about the applications of nuclear magnetic resonance. So this is one of the most powerful methods for analyzing chemical samples and biological samples and medicines also. So it gives a structural information on a range of different elements in a molecules, including hydrogen, carbon, and phosphorus, and many other, how they are arranged. So from that, you can get the structural information in a molecule, how the hydrogen and the carbon are placed. And for a structural determination of a molecule in solution also, you can find out. And it gives an information regarding the motion in a molecules and structural flexibility and how they interact in a chemical reaction. And using this, we can determine the shapes and structures of large complex nuclei. So that is a proteins, and that how the proteins are a twist or a coil, all these very complex structure also you can analyze. And you can evaluate the portions of solid and liquid components in a fatty foodstuffs and low fat spreads. So that means that you can evaluate the proportions of solid and liquid components. So in any tissue or any other foodstuffs or fatty foodstuffs or anything way, the solid component and liquid component also you can evaluate how much percentage of solid component is there and how much liquid component is there. And this is also useful for a medicine and pharmaceutical sciences. And this type of a closely body scanning closely related to that is MRI. And tissues, in any tissue, the abnormalities. So that is a malignant and normal tissues you can identify, or you can distinguish the normal and malignant tissues. With that, you can diagnose the cancer and other growth. And pH control for a diabetic patients also. You can how you can control the pH, that also you can. Another application is a quantum computing. This is for a technically even in the not only in the chemical and biological sciences, you have in a computer application also. This is a quantum computing. So this is using quantum computing, you can drastically increase the present computing powers and revolutionize how we so far using computers for scientific problem solving. Because all these you can call it as a qubits. And that type of a molecular level or a atomic level, how the this stores energy. If there is any small difference in energy, that also everything we can identify using a qubits. So by defining a qubit, you can use this for a storing and computing the overall quantum. We call it as a quantum computing. Not an optical computing, but it is a quantum computing. Okay. And another one is how you are getting the different additional information from NMR spectra. So these are all the we will calculate this chemical shift and spin coupling and relaxation time and area under the peak and signal intensity. So these are all different concepts from where you will get the information. So about local chemical environment of atom within a molecule. So if you consider one molecule, within that molecule, how the chemical environment of atoms changes locally. So from that, you can calculate. So CH3, CH2, and CH, the type of a, how the, what type of a group, that is a methyl, ethyl, whatever the group associated with a large molecule, that you can identify with a triple, that is, lines or a double lines, that is the peaks, how many peaks are you are getting from a NMR spectra. From that, we can calculate the chemical shift and we can estimate whether it is a CH3 or CH2 associated with the molecule. And spin-spin coupling constant. So this also, that is the information about a adjacent atoms. So this is only how the chemical environment, and here it looks further, that's the adjacent atoms and the splitting of the peaks. By splitting that peak, you can identify what is the adjacent atoms. And molecular dynamics also, you can get the information using relaxation time. And also, by integrating, you can get the number of atoms in a peak. So for a peak, if you have a 3 atoms, CH3, CH2, how many atoms present? Hydrogen atoms. Similarly, any other atoms present with that, you can calculate by calculating the area under peak. And another important one is that quantitative information. So that is regarding atomic ratios within a molecule that can be helpful in determining the molecular structure and proportions of different compounds in a mixture. So in a mixture, that means what are the different compounds are mixed together to form a mixture. So that you can different proportions, with the different proportions, you can form a mixture. So within that also, you can estimate from the signal intensity how much percentage it has within a mixture. And not only from the molecular structure, you can quantitative information also, you can calculate using the signal intensity. So this the information, this type of information you usually you will get from the NMR spectra. Okay. So look further here. Again, we will come back to the what is the basic principle. So basic principle of nuclear magnetic resonance. So when a nucleus that possesses a magnetic moment, so usually hydrogen and carbon, they possess a magnetic moment. And if you place such a nuclei in a strong magnetic field, it will begin to precesses. That means it precesses at a particular frequency. That means it rotates. How the Earth is rotating about its axis, that is a precession. So how the top will precesses around its axis, or how the Earth spins around its own axis, that is a precesses. So this precision is fundamental attribute of nuclei that allows us to use NMR. So how do we get from the spinning proton to an NMR spectrum? So we can use to interpret the structure of a molecule, and that is what ethanol or whatever that means. So we can take any example and we can calculate how the structural environment within that a particular molecule. So here, this is a blue one is a magnetic field. Within magnetic field, this hydrogen nucleus has its own magnetic moment. So it precesses around its own axis. And under external magnetic field, it will try to reorient. So if the sample is placed in a magnetic field and irradiated means if you expose to a RF frequency, that means radio waves. So if you select a particular radio wave frequency, radio waves, and if you expose, or that means if you irradiate then the same frequency as the precision frequency, it will be absorbed and you will get the NMR spectrum. So that means it is a magnetic field is irradiated, and how it is at what frequency radio waves you are applying, that depends on the precision frequency. So exactly the precision frequency will match with the irradiated of radio waves. So that's why you will get a resonance. That is a resonance. We call it as a resonance because these two frequencies will match. So NMR spectrum, this is, for example, so here it is OH, CH2 and CH3. So here 3 hydrogen. So you have a intensity is more. So here it is intensity less. Here it is only 1. So it is a intensity further less. So here we are using this one. So the signal intensity, and it will give a quantitative information, how many atomic ratios within a molecules. So that's why this is the example. So CH3, CH2 and OH. So the intensity, this is of an ethanol. CH3, CH2, OH. So this is how we will get the, so if it is a known one, you are getting the information. Even if it is unknown, you have some mechanism to calculate what are the different groups present within a molecule. From that, you can estimate the molecular structure. Then we are moving to what is how do you record this NMR spectrum using a NMR spectrometer? So this is the instrument. What is the instrument and what it contains? So that means there are different spectrometers, NMR spectrometers, and simple technique is the single coil method that we will describe here. Okay, so that means what usually it consists of, inside an NMR instrument, the sample is exposed to a very strong magnetic field, roughly around 1 to 20 Tesla. By comparison, a refrigerator magnet is approximately 5 milli Tesla and about 0.3 Tesla for a strong niobium magnet. Within the NMR tube, the sample nuclei align with the field in either alpha orientation or beta orientation. So the NMR tube sits inside an area surrounded by large magnet, a radio frequency transmitter, and a coil to receive radio frequency signal. So I will give you the schematic diagram of NMR spectrometer. This is a schematic diagram of a NMR spectrometer. So here, see, this is the RF transmitter. This is the transmitter. And this is this coil. This coil thing is see here, this is the tube containing the sample tube. So we can keep the sample inside this tube, and around this tube, you have this radio frequency receiver and amplifier. And here you have a magnetic poles. These are the two strong magnetic poles. And these are the sweep coils and the entire thing is controlled by a console and recorder. That is the, you have a computer control, and you have recording and for a chart also, that means for a graph, or for a storing, you need a computer. So that means you have completely computer controlled console. So this is an electromagnets, sorry, these magnets are very homogeneous and static magnetic field it creates. And that is a slowly vary the magnetic field around the resonance field with B naught. And a low frequency magnetic field modulation arrangement to the pole pieces of the magnet to display the signal within this console, and RF source for inducing the dipole transitions. To induce, say, nuclear dipole transitions, we are using this radio frequency transmitter. So, and with an RF amplifier, and you have a detector. So the detector and all completely connected to the console. And what's the amplifier? So the amplifier uses to tune to the frequency of a modulation frequency. So this is the general schematic diagram, and working, you can simply how it works, that you write as a 2 or 3 paragraphs. That is enough. So this is the schematic diagram of NMR spectrometer of a single coil method. So this is using a single coil spectrometer. So as I said, these are all highly stable magnet, and you have a sample probe and radio frequency radiation source and phase sensitive detector and data processing unit or computer. So with this, you can record the NMR spectrum. So you have a double coil method also. You can simply, if you are interested, you can go through the double coil method. Otherwise, you can satisfy with the single coil method for the examination purpose. As the syllabus is very exhaustive, so we will cover only the major important concepts what are required for you. Okay, so usually from this, the output voltage that is converted into a DC by the detector, and it will be inconvenient to amplify the DC signal. So in order to get an AC signal after detecting the magnetic field will be modulated by an AC magnetic field. So this is the type of a technique. So this we can achieve a type of a copper winding. So on the pole pieces, and that means here copper winding. So sending the alternative current of low frequency. So somewhere around 50 hertz through the coil. So then the output of the oscillator will be modulated by the NMR signal with the modulation frequency. Okay. So this signal is further amplified and displayed on the monitor of a computer monitor or whatever is attached to that one. So that means a steady magnetic field is modulated while keeping radio frequency constant. We can keep magnetic field constant and modulate radio frequency. So that means the simpler way, the magnetic field we can vary and keeping the RF radio frequency constant. So both the ways you can do, but simplification, we can vary the magnetic field. Variation of the magnetic field is usually a little bit less technology is involved. Okay. So from that, the amplitude of the signal is here, the amplitude of the signal, what we are getting from the sample is proportional to the changes in the susceptibility and phase of the, how the phase changes with the susceptibility. So that we can use, and using a different modes, and absorption mode is preferred. So how much energy is absorbed? So the spectrometer gives a faithful reproduction of the susceptibility with the magnetic field at fixed frequency. So here it should satisfy the two conditions. Though that means the steady magnetic field must be very homogeneous, so that the entire material under investigation almost nearly as possible in the same field. So the key to keep the whole sample in the same magnetic field, that is a homogeneous field, is also you have to achieve. That is the one condition. So for homogeneity, so 1 to 10 to the power 8 Gauss. So if you increase this type of inhomogeneity, if increases, what will happen? You will get an additional line width will be broadened, and you will get an additional line, or that line will become broadened. So that's why to distinguish the true line from this broadened will become difficult. So that is the one condition. And another condition is so the second condition, that is that if the resonant signal is to reproduce the variation of chi double prime with the field, must be very slowly. That variation must be very slow if the variation with the magnetic field. So this is nothing but steady state condition. So that these two, steady state condition and that is the homogeneity of the magnetic field. These two must satisfy to get a good spectrum. That is the important for this one. Okay. So next we will move on to the relaxation processes. So these relaxation processes, usually we are giving a radiation, that's radio wave radiation, that will be absorbed. So the population distribution gets disturbed. So once the radiation is absorbed by the sample, so that's as the population difference between the two spin states very small, the population of a lower and higher energy would become equal after absorption of radiation for some time. It means that resonant signal has achieved and saturation, and no more energy can be absorbed. So that means if it equals, then whatever the energy is absorbed, and it will be, it will not take any energy further. So the saturation, you will get the saturation state. So, sorry. So that for a competing phenomena is a competition that do not allow at this stage to come. These are called relaxation mechanism, which opposes this mechanism. That is the saturation mechanism. This is nothing but a relaxation. So in the process of relaxation, the nuclear spins in the excited state relax down to a lower energy state, through radiation-less processes. So this type of a radiation-less processes, you have two. One is spin lattice relaxation. Another one is the spin-spin relaxation. So let us see what is the difference between these two and how do you distinguish between these two. So to maintain the population difference in the energy levels, the rate of relaxation from the excited state to a lower energy level must be greater than the rate at which the radio frequency is absorbed. So that means to maintain the population difference in the energy levels, the rate of relaxation from the excited state to the lower energy level must be greater than the rate at which the radio frequency is absorbed. And this process, the spin lattice relaxation process, involves the transfer of energy from the nuclear spin in the high energy state to the molecular lattice. So the random motion of adjacent nuclei in the lattice, it set up a fluctuation in the magnetic field. So it fluctuates, the magnetic field will be fluctuated because of the molecular random motion of the adjacent nuclei. So the adjacent nuclei, if they get disturbed or they are moving, so the magnetic field also get fluctuated. So that leads to its interaction with the magnetic dipole of the excited nucleus. So this results in the transfer of energy from an excited nucleus to the neighboring atoms. So further, that disturbance, that energy will be transferred to the neighboring atoms. This is sometimes called longitudinal relaxation. The transferring to the nearby atoms is called longitudinal relaxation. So nucleus returns to its original low energy state from the excited state, and the excess nuclei are maintained in the low energy state. So, which is a necessary condition for energy to be absorbed. So when it will get, the energy will be absorbed. So whatever that small energy, it will, if it transfers from the excited nucleus to the neighboring atoms, if it transfers that energy, what will happen? It is in a position to absorb some more energy. So that is how it happens. So that's a necessary condition for energy to be absorbed. So this is a spin lattice relaxation. Is it clear? If you have any clarification, you can ask me even in the end of the session. So if you come to the spin-spin relaxation mechanism, this involves a mutual exchange of spins by two precessing nuclei in close proximity to each other. So if the two are spinning very closely, so what will happen? They mutually exchange the energy. So if there are two nuclei, then one of these can flip down and the other may up. So by mutual exchange of spins. So if it is in the up direction, it will come down, and another which is move is a other down spin, it will go to the up spin. So they exchange. So this type of a relaxation mechanism, we call it as a transverse relaxation. So one is a longitudinal relaxation, is another one is a transverse relaxation. So here it is a longitudinal relaxation in the spin lattice mechanism, and this is the transverse relaxation. So that is a vertically, and if it transfers energy to the neighboring atom by transferring a sum of energy, what it absorbs. So here these mutually exchange, they spins up and down, this will become a transverse relaxation. So it shortens the lifetime of an individual nucleus. That means from the high energy state to the low energy state. So the type of a lifetime of an individual nucleus in a higher energy, but does not contribute to the maintenance of the required excess in the lower energy state. So due to this or these relaxation mechanism, the excited states have a small lifetime, because whatever that energy is absorbed and it is going to the high energy state and it is transferring via transverse relaxation or longitudinal relaxation quickly. So that means it is not maintaining at that particular higher energy state for a long time. So that means the energy level lifetime decreases with this relaxation mechanisms. So due to the relaxation mechanisms, the excited state have a small lifetime. So the lifetime decreases. So of excited inversely proportional to the width of the absorption line. So if width of the absorption line is broad, that means if the more energy is absorbed, the lifetime will be very short. So because of by going through all these discussion, that means as a result of inverse proportionality between the line width and the lifetime. So the line width and lifetime, these are all inversely proportional. So that means if you find a sharp resonance, then they are of a long-lived excited states, and broadened lines for a short-lived states. So that means if it is absorbing more and more energy and it is transferring to the relaxing by transferring energy in the transverse mode or transferring energy in the longitudinal mode, it will become a broad lines. So both spin and spin lattice relaxation processes contribute to the line width. Both are the contribution, both are same, but one is via transverse relaxation, another one is via longitudinal relaxation. Okay. So is it clear? Yeah. Now we are moving to the these are the practical how you are exploiting this NMR in a chemistry or even the material science, wherever you are using. So this chemical shift describes the behavior of nuclei in the presence of a magnetic field. So technically it is only for a isolated nuclei. Okay, so that isolated is not, it is almost impossible, but we will apply some condition. So in the resonance condition, nuclei mu is equal to Gn mu n B naught by H. So this implies that all the nuclei of a given type in a sample should absorb the energy corresponding to the above nu. So nu value, this is nu, not B, nu value. So if this was the case, NMR spectroscopy would have been no use. Okay. So in real systems, we do not deal with the bare nuclei, or that means isolated nuclei. So they compulsorily surrounded by electrons and their presence. So nuclei, that means you can't take out nuclei separately from the atom. There is no existence. So with the electrons only, but we can study the inside structure of nuclei without considering the electrons. By broadly, we are not taking the electron interactions on the nuclei. But it is not possible to isolate separately the nuclei. That means neutrons and protons without electrons is not possible to consider. You can consider, but it's not practically not possible. So their presence can modify the fixed that means field experienced by the nuclei. That means if you consider nuclei without electrons, what is the field? So if you consider the nuclei with the electrons, how the field experience. So here you will get a shielding or de-shielding. That means electrons, they may shield to some extent external field. How the nuclei are experiencing the external field. So that is the shielding mechanism. So all even in the chemistry, first ionization potential, second ionization potential, that means in an atom, what is the definition of a ionization potential? That is if you consider a neutral atom. So the energy required to remove the valence electron, outermost electron from the neutral atom is called a first ionization potential. So from the singly ionized atom, if you remove the valence electron or outermost electron from the singly ionized atom, that energy required to remove is called second ionization potential. So why the first ionization potential is less when compared to the second ionization potential? That you can explain on the basis of shielding of electrons. So the outermost electron is loosely bound because all these electrons are shielded and outermost is loosely bound. That's why you can simply remove the outermost electrons quickly when compared to the innermost electrons. So similarly, this nuclei, bare nuclei is not possible, and you have to consider the electrons completely within the system. So the field experienced by the nuclei that is associated with electrons, then you will get a shielding and de-shielding effect. So how the electrons will shield the magnetic field and how they de-shield the magnetic field, what the nuclei experience. So this makes the nuclei come to a resonance at a different frequencies. Because of the shielding and de-shielding effects, nuclei will come to resonance at a different frequencies. So electrons circulating around the nucleus. So if you consider, so nucleus means it's a proton. In the hydrogen atom, you have one electron. So usually it is of a spherical in shape. And it produces an induced magnetic field, BIND. So which opposes the applied field B0. So this is applied field and this is the induced magnetic field. Always this will oppose the magnetic field. So therefore, magnetic field experienced by the proton in a molecule placed in a magnetic field of strength B is always less because of shielding or screening of the nucleus by the surrounding electrons. So nucleus is surrounded by electrons. That's why the nuclei present in the nucleus are shielded by the electrons. So the effective magnetic field experiences by the nucleus, you can calculate using this. B effective is B0, that is applied, minus B induced. So always B induced is less than the applied. So you will get a B effective. So if the induced field, on the other hand, is proportional to the applied field, definitely it will be proportional to the applied field. And we can use the proportionality constant sigma, and we call it as a shielding constant. So, and this is a measure of extent of shielding by the nucleus. Shielding of nucleus by the electrons. So we are shielding the nucleus by the electrons. So by substituting this value, and we will get the this equation. So this B induced is equal to this one. So this is nothing but B naught 1 minus sigma. So thus, in the presence of an extra nuclear electronic environment, the resonance condition you can modify using this. So this resonance condition, what previously mu is Gn mu n V naught by H. So it will be modified by Gn mu n V naught 1 minus sigma by H bar. So therefore, the nucleus in a resonance at a lower field. That means due to the shielding of identical nuclei. So identical nuclei means usually you have a which have different chemical environment resonate at different values of the frequencies or applied field. These values being characteristic of chemical environment and that can be used to identify the various types of environment in which the proton is present. So proton is associated with what type of a chemical environment. So from that, you can identify the position of resonance, and due to difference in chemical environment, it is called the chemical shift. So that chemical shift, the delta mu E. So that's why these values being characteristic of chemical environment can be used to identify various types of environment in which the proton, so proton is presented in a different type of chemical environment, that is CH3, CH4. So the type of the proton is associated with a different, so the ethyl alcohol or methyl alcohol. So the chemical environment of a proton is different. So that you can identify using the chemical shift. That is the major application of this chemical shift. Okay. So standard chemical shift. So that means how you will use that standard one. So that means you have to compare with some standard value. So here usually we will take the TMS is the standard for a chemical shift data. So what is TMS? See, this is tetramethylsilane is a standard. Okay. So TMS is tetramethylsilane. So it has a following characteristics. Why you are choosing the TMS as a standard? So usually we will use some of the for preparing solutions. Always we use a standard. This is the water for a solvent or some other solvent we will take, because it is not going to react with the compounds what we are mixing, and it will aid to take as a reference. So it gives a strong and short signal at very high field. Therefore, it does not interfere with the signals of all other type of protons in different organic molecules. So as they absorb at a lower field. So all these will absorb the energy very low when compared to the TMS. That is one of the prime reason why you are taking TMS as a standard one. Okay. This is the one. And all the 12 protons chemically and magnetically equivalent in the TMS. So this gives a reasonably intense signal even at a very low concentration. And another one is it has a low boiling point, 27 degrees centigrade. So it is soluble in most organic solvents. Hence, it can be easily removed or separated from other organic compounds or solvents after the spectrum is recorded. So you will get back the original Hello. Hello.
Yes, sir.
Yeah, audible. So some disturbance, some discrepancy. So that TMS, why you are using the TMS as a standard? That means it is a low boiling point and all the protons are magnetically equivalent, and it absorbs at a higher field. So these are the three important aspects. And another one is highly inert. Usually that should be, it is not going to react with any compounds. So these are all the important characteristics for which we are using TMS as a standard for chemical shift. So what are the factors affect the chemical shift? So that means from this, you can identify the previously what I observed. This is the how from this, just only once I will go back and this. You have in a ethyl alcohol or ethanol. So OH, CH2 and CH3. So these are all the, so from here, these two OH2, CH3, you have almost 1.75 chemical shift. And this is CH2 to CH3, somewhere around you have 2.45. So that you can calculate and you can estimate. So that means what are the things that will affect the chemical shift? So anisotropy of chemical bonds and electronegativity and hydrogen bonds. So in the hydrogen bonds, that means OH and CH2 and CH3 are different hydrogen bonds. So that's why you will get a different chemical shift. So in case of hydrogen bonding, H atom is shared by two electronegative atoms. It is highly de-shielded and the resonance occurs at a low field corresponding to high delta value observed. So that means all these alcohol, amines and other, they have a varying degree of hydrogen bonding. Thereby you can identify that using the chemical shift. Okay. So this with this I will try to conclude, or any other doubts and important as you told, important questions, those things we will discuss tomorrow. Okay. Uh, in each block, what are the things and how do you prepare and what should be the strategy? Those things I will discuss tomorrow, or you want to discuss, that is better to discuss tomorrow. Okay. So I will quickly go through the block equations. Anyway, I am going to share this PPT with you and this block equations. So this is another one is a important theoretical equations, and where you are getting the imaging. You can predict the imaging and contrast from this type of equations. So these are all a coupled differential equations that describes the behavior of net magnetization under influence of B naught, that is the applied external magnetic field. So here, if you start with a spin magnetic field and there is no net force on the dipole, so concerned with the effect of torque of the angular momentum. So that torque you can calculate using dl by dt is sum of d tau omega mu b. And here, that is the angular momentum L and magnetic momentum mu, and mu for a spin, and that is a gyromagnetic ratio is gamma L. So that equation will become a d by dt of mu bar and gamma mu cross b bar. So for population of spins, or net magnetic moment is given by that sum of mu I, and this will be resulting net magnetization. dm by dt and is a vector, and B, that is the magnetic field, and we will consider the uniform magnetic field oriented in the z direction and B naught z in the absence of interaction between the spins. That means no relaxation mechanism. So initially we will consider no relaxation mechanism is involved to make it simplify. So these three equations by this cross product, and we can use. So it's a small mathematical jugglery, and that you have to derive in a systematic way. That is x and y and z directions in the three directions. So these are the, there is omega my and minus here. Consider the sign, initial important one. There's a minus omega naught mx, and in the z direction it is a 0. So this steady state solution without relaxation, that you have to keep it in mind. This is we are not considering any relaxation mechanism. So how precision is determined by the cross product. Since these coupled equations, you have a cos omega t into sin omega t. So with this x and t, how it changes? There's a cos omega t into sin omega t. And if you want to add the relaxation term, you have to start with the longitudinal magnetization mz. So that mz is 1 by t. This is where you are considering the relaxation mechanism. So MO is the steady state magnetization, and the Z is the current magnetization. Both you have to consider. So, and the solution for this first order differential equation, and that is mz e to the power minus dt by t1, and m naught 1 minus e to the power minus t by t1, e small t by t1. So always we have that constant b is equal to b naught z. So these solutions, they describe only the relaxation after a pulse. So first, the after perturbation from the equilibrium. So that means first, we are not considering the relaxation. Only after one pulse, you can expect the relaxation mechanism will take place. And this is accounted for realizing during the RF frequency, you have a B1X and B1Y and B0Z. Okay. So from this, you will get the block equations within this form mzt and em perpendicular. So that is m perpendicular e to the power minus here by t2, and here it is a t1. And briefly we will remind. So this is what, from where you are getting this Rm cross B. That is the starting one. So from this only we are starting, and we are deriving at the final equations of these steady state solutions. So steady state solutions are important. Okay. Yeah. So here, sorry, yeah, any other discussions, we will meet tomorrow. Keep all your discussions and the questions from tomorrow. Right now, sorry for I have some other work. I'm leaving. Any
Okay, sir.
yeah, you keep all the doubts and everything for tomorrow. We will discuss tomorrow. Okay.
Okay, sir.
Yeah, thank you.